So Erich, I'll give a short introduction before I pass you on. Yeah.
Just one comment. Remember that the YouTube stream that is running is like 20 seconds behind, right? So if questions come a little later, then right, be prepared.
Okay.
So, but I'm not meant to be monitoring the YouTube stream. Is that correct, Holger?
No, correct. But if some people see it in the YouTube, then they go to Slack.
Yeah.
There will be a delay. Yeah. Good.
Just what is the what's the policy on starting?
You are the chair, and
okay.
I wouldn't mind starting.
Yeah. Okay. So let me get
in the audience.
Okay. 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 So welcome to the joint LICS ICALP tutorial session, and the tutorial will be given by Erich Graedel. So Erich is professor for mathematical foundations of computer science at Aachen University, and he's been in that position since '93. He got his PhD in Basel in 1987, and he's since then has kind of worked across many a wide variety of topics in computational logic, algorithmic model theory, infinite games. He's known for many results. I mean, among which one could mention complexity of the two variable fragment of first order logic, complexity of the decision problem for the guarded fragment, finite model property, but very many different areas of logic, descriptive complexity, transitive closure logic, dependence logic. He's also author of many books, among which is the book with Gerowicz and Berger, the classical decision problem, the kind of definitive reference on the complexity of the decision problem for first order logic. And 20 years ago, he wrote a paper in ICALP on automatic structures. And I think in this tutorial, he's going to revisit that topic. So it wasn't the first paper on automatic structures, but I think a paper that introduced automatic structures to the LICS community. So I'm very happy to have Erich talk about that now. Thank you very much.
Well, thank you, and thanks for the opportunity to give this tutorial here. So, oh, now I have a problem. Okay, so in a nutshell, what are automatic structures? These are structures that admit a finite presentation by automata, which means that the universe and all relations of the automatic structure are recognizable by a finite automata that work synchronously over their inputs. So in principle, we can use any kind of automata over finite or infinite words, finite or infinite trees, or even more general objects, as long as these are effectively closed under all first-order operations and their emptiness problem is decidable. Now, this means then that given an automatic presentation of a structure A and a first-order formula, phi with free variables x, one can effectively construct an automaton that recognizes the relation defined by phi on A. And as a further consequence, we have that every automatic structure has a decidable first-order theory. Now, here is an outline of this tutorial. I will give some remarks on the early history up to that paper from 2000 that Ben mentioned. I will show different variants of automatic structures, give definitions and examples. I will then discuss the algorithmic problems associated with automatic structures, and I will present a model-theoretic characterization via interpretations, which is basically what we did 20 years ago. Further, I will comment on methods to prove that the structure is not automatic, which is relatively simple in cases of word automatic structure, but the analysis of the model-theoretic properties of omega automatic structures that are used for such result is much more difficult. At the end, I will address the still open question whether the field of reals, which has a decidable first-order theory, is automatic in some sense. Now, the roots of automatic structures go back to the decision procedures for logical theories in the beginning of the 1960s due to Büchi, Elgot, and Rabin. The first explicit definitions of automatic structures appeared in the PhD thesis of Bernard Hodgson in 1976 and two subsequent papers from the 80s. Now, already in that thesis, Hodgson first considers the notion of structures whose theories are decidable by finite automata, and then goes on to an explicit definition of automatic structures and already also omega automatic structures called structure macro-automatique in his thesis. And he gives a number of examples of automatic and omega automatic structures, different types of linear orders, Pressburg arithmetics, the addition of p-adic numbers, etc., and shows that products and powers of automatic structures have theories that are decidable by automata. It's a very impressive work, but unfortunately, this work went largely unnoticed. And in fact, I have to offer an apology here because also in my own work, I did not notice what Bernard Hodgson had done until very recently. A different kind of early area where automatic structures have studied are automatic groups. Now, automatic groups have been developed around 1990 in computational group theory, and these are finitely generated groups whose Cayley graphs are presentable by finite automata in a specific way. The importance of this notion in computational group theory comes from the fact that automatic groups admit efficient algorithms for certain problems that are undecidable in the general case. In particular, the word problem for automatic groups can be solved in quadratic time. There are also important differences between automatic groups and the general notions of automatic structures that we study now. First of all, not the group structure itself is an automatic structure, but the Cayley graph. Further, the automatic presentation is restricted. We are not free to represent the Cayley graph in any automatic way. And as a consequence, not even all groups with automatic Cayley graphs are automatic groups in the sense of computational group theory. As a consequence, there has not been really much interaction between the study of automatic groups in computational group theory with the study of automatic structures in logic and computer science. But still, it is an important reference. Now, almost 20 years after the work of Hodgson, automatic structures were reinvented by Kusainov and Nero in a paper from 1995. And this is what really started the research in automatic structures as we know them now. So the motivation of Kusainov and Nero came from recursive model theory. So from structures that are not presented by finite automata, but presented by Turing machine, and the restricted version based on p-time computability. Now, recursive structures and also p-time structures in that sense are mathematically interesting, But the algorithmic content is still rather limited. In fact, only the quantifier-free part of their series is in general decidable. Even the existential formulae give rise to recursively enumerable sets and are not decidable. Now, in contrast, and it is nicely put in the paper by Kusainov and Nero, that the research on automatic structures, unlike research on recursive and p-time structures, concentrates on positive results. So here are some of the contributions in the paper by Kusainov and Nero. So say, in fact, not just one, but several variants, how structures can be presented by automaton finite words, and they already propose the extension to 3 automatic structures. They provided further examples of automatic structures like finite generated abelian groups and so on. The most important is probably the observation that the computation graph of any Turing machine is an automatic graph. They also observed that for word automatic structures, injective presentations are as powerful as general presentations, so there is no restriction to impose injectivity of the presentation. And they explicitly spelled out the very influential program to classify the automatic structures inside specific algebraic domains, to determine which linear orders are automatic, which Boolean algebras are automatic, and so on. Now, automatic structures came to LICS in the paper that Ben mentioned, the joint paper with Achim Blumensaat at LICS 2000. And our motivation was something completely different. We came, in a sense, from below, not from above. So it was part of a general project to extend the approach and methods of finite model theory to infinite structures that admit finite presentations. And the automatic structures are just one kind of such infinite structures where the presentation is done by finite automata. So contributions were a relatively detailed complexity analysis of the first-order theory of automatic structures, the study of extensions of first-order logic in terms of decidability, for instance, by the quantifier that there exist infinitely many x's, composition theorems for automatic structures, undecidability result for properties that are not first-order definable, such as isomorphism and connectedness, and methods for establishing that certain structures are not automatic. In fact, these had already been in some part established by Kusainov and Nero, but they were generalized in our paper. Now, but what I consider the most important contribution of that paper is the model-theoretic characterization of automatic structures in terms of first-order interpretations. I will talk about that later. After 2000, the field really expanded very much. The area has become very rich with a large amount of research on different variants of automatic structure. In fact, also quite a number of papers that have been published at LICS. We wrote a survey almost 10 years ago, not just on automatic structures, but also on other kinds of automata-based presentations of infinite structures. And there are also 2 earlier survey papers on the word automatic case, one by Kusainov and Minnis in the tutorial at the Logic Colloquium, and a survey article by Sasha Rubin. I think it should also be mentioned that a very relevant part of all this work on automatic structures has been accomplished by students. So there are a number of very nice theses where key results on automatic structures have been found and published. So a lot to read. Now, let me now give a precise definition of automatic structures in the sense of structures presented by automata on finite words. So a structure, which we always write relationally, is word automatic if there exists a regular language and a surjective function from the words in that language to the element of the structure. Now, the words in the regular language provides names for the elements of the structure, and of course, every element of the structure should have a name, but it's quite okay to have several names for one and the same element of the structure, so the function need in general not be injective. But if it isn't, it should be recognizable by an automaton where 2 words name the same element. so the relation, the equality relation must be recognizable by an automaton, and also all tuples of words that encode a tuple in some of the relation must be recognizable by a finite automata. So an automatic presentation, a finite automatic presentation of an in general infinite structure is just given by the list of automata that recognize the regular language, the equality relation, and the relations of the structure. Now, perhaps it should be said explicitly what it means that an automaton recognizes a relation of words. Now, we are used to automaton recognizing individual words. Now, to recognize a relation, we expand the alphabet. So first of all, we add a blank symbol to, so that we can fill up the words that have not the maximal length. So in general, words may have different lengths, so we fill them up by blanks so that they all have the same length. And then we consider a tuple of symbols as one symbol and let an automaton process these from left to right in a synchronous way. So formally, the automaton accepts a word in this expanded alphabet, and this gives us a definition that an automaton recognizes a relation of words. Here are some of the most important examples of automatic structure. It's a standard example is the additive theory of the natural number. So we can encode a natural number by binary representation, starting with the least significant bit. And then it is obvious that we can recognize addition, right? We just have to, we scan a triple UVW from left to right, remembering the carry bit and check whether at each point WI is UI plus VI plus CI. CI is the carry bit modulo 2, and in this way we can decide whether W is indeed the sum of U and V. So this is, in some sense, one of the simplest automatic structures. Obviously, every finite structure is automatic, and as already mentioned, the configuration graph of any Turing machine is automatic. Now, there are also more powerful automatic structures, structures that we call universal automatic structures, for a reason that will become clear later. For instance, when you extend the additive theory of the natural number with a restricted divisibility relation, saying that X is a power of P that divides Y. Then this expanded structure is still an automatic structure. Instead of binary representation, we use p-ary representation, which of course still gives us a possibility to recognize addition by an automaton. But then it's also very simple to recognize this restricted divisibility relation by an automaton because the words are then represented in the way displayed here. A second kind of class of universal automatic structures are tree structures. So the nodes are words, finite words over an alphabet of M symbols. We have the successor functions written relationally for each of the symbols. We have the prefix relation, and we have the equal level predicate, so two words have the same length. This also is a structure that can easily be seen to be an automatic structure. Now, in a similar way, we can define omega automatic structures. These no longer need to be countable because we consider as the universe is encoded by an omega regular language of infinite words. So we have a omega regular language. We still have a subjective function from this language into the universe of the structure, and we have precisely the analogous definition, but now the relations representing equality and individual relations of the structures are omega regular, that is recognizable by synchronously operating Büchi automata. Of course, every automatic structure is also omega automatic, but more interesting omega automatic structures are the additive structure of the real. and the expansion by order by, again, restricted divisibility relation of the form that x is m to the k for some integer k, and y is r times x, where r again can be an arbitrary integer. Also, the tree structures can be expanded to omega tree structures, where we do not just take the finite words, but the finite and the infinite ones. We still have successor relations, obviously defined only on the finite words. We have the prefix relation, which can relate both finite and infinite words, and again, the equal length predicate. Again, it is not difficult to see that this is an omega automatic structure. Now let's get back to this notion of automatic groups and explain this in a bit more detail. Now, an automatic group is a countable group with a finite set of semigroup generators. So we then have a canonical surjective map, mapping a word over the semigroup generators to the group elements. So the Cayley graph, defined by the group and the set of semigroup generators, is just the graph whose vertices are the group elements, and we have an edge labeled S from G to H if G times S equals H. Now, by definition, G is an automatic group if there exists a finite set of semigroup generators such that this Cayley graph is an automatic structure with a presentation by a regular language over that alphabet of semigroup generators, but with the important restriction that the map from the language into the group must be the canonical map. So we are not free to name the group elements in any way by a word over the semigroup generator, but it has to be the canonical map that maps a product of generators to the group elements that it defines in the obvious way. So here is an example, as the groups Z times Z. The semigroup generators are just +1 and -1 in both dimensions. So here is a picture of this Cayley graph. And we represent it by the regular language where we take all the x's first, as we go a certain step, a certain number of steps to the right or to the left, and then we go a certain number of steps up or down. So the words that remain are really the words displayed here. Now, an important property of such automatic groups is what is called the K-fellow travel property. So assume that we have an automatic group with an automatic presentation based on the language L delta. Then it is the case that when we take any two words, U and V, which are close together in the sense they're either the same or their distance is at most 1, then also in the way from the beginning to the end, these two words are never further away than a fixed constant k, which is related to the number of states in the automaton that represents the group. And this property, this K-fellow travel property, in fact characterizes automatic groups in the following sense. A group is automatic if for some set of semigroup generators and some case there is a regular language such that the canonical map is surjective and satisfies the K-fellow travel property. So this K-fellow travel property then implies that the relations of the Cayley graphs can in fact all be recognized by a finite automaton. And this K-fellow travel property is crucial for many results in automatic group theory, and in some sense is responsible for differences between automatic groups and automatic structures in general. Now, by definition, if we have an automatic group, then for some set of semigroup generators, the Cayley graph is an automatic graph. But the converse is not true, and a counterexample is the so-called Heisenberg group, which is a group of affine transformations on set 3, so generated by 3 functions alpha, beta, gamma. Now, the precise definition of these functions is not important. It is important that they are defined in such a way such that this Cayley graph is obviously first-order interpretable in Pressburg arithmetic. So since this is an automatic structure, the Cayley graph of this Heisenberg group is also an automatic graph, but it is known that it is not, the Heisenberg group is not an automatic group in the sense of computational group theory. So let's now move to algorithmic problems concerning first-order logic. Now, standard models of automata are effectively closed on the first-order operations: union, intersection, complementation, projection, and have a decidable emptiness problem. And this immediately implies that every automatic structure has a decidable first-order theory. So the question arises, can we extend such results beyond first-order logic? This was a typical question we asked from a finite model theory perspective. And there are positive and negative results concerning that question. The positive results mostly concern counting quantifiers. So when we extend first-order logic by counting quantifiers of the form, there exist infinitely many x such that there exist k mod m many x such that there exist uncountably many x, or of course also dual, there exist at most countably many x. The last, of course, make only sense on omega automatic structures. Then the automata theoretic approach, so build an automaton that represents the relation defined by a structure, still can be done. And so we can still effectively present all relations defined by a formula in that extended logic by a finite automaton. So also the first order theory with counting of every automatic or omega automatic structure will still be decidable. There are also other possible results on regularity preserving Ramsey quantifiers that have also important definability consequences. But I will not talk about this here, but you will find it in the paper. Now, on the other side, problems like query evaluation and model checking are undecidable for extension of first-order logic, such as transitive closure logics, fixed point logics, or monadic second-order logics on, of course, not all, but on certain automatic structures. And the reason for this is, well, first of all, with these logics, one can define multiplication from addition. So once we have addition, so which is an automatic structure, then we add multiplication, and then we get a structure where everything is undecidable. So with fixed point or transitive closures, it's not difficult to find multiplication. Now, a further reason is that, as pointed out before, the configuration graph of any Turing machine is an automatic graph. And this means that any logic that is strong enough for reachability can express a halting problem and therefore does not admit effective evaluation on all automatic structures. Concerning complexity, there are automatic structures where the first order theory, although decidable, is not elementary. Now we know that for Pressburg arithmetic as such, it is it's complicated, but it is elementary. But when we add this restricted divisibility relation, or when we consider these three structures that admit the equal length predicate, then the first order theory is not elementary. Elementary complexity results on the other side have been obtained, for instance, by Kuske and Lorai for automatic structures and even three automatic structures where the Geifmann graph has a bounded degree. So there are many cases where this phenomenon that the complexity is non-elementary does not appear, but also in these cases the complexity is still rather high. And in fact, for every natural numbers, there exist automatic structures whose first order theory is precisely on the nth level of this exponential hierarchy. First, there is a relative detailed complexity analysis for fragments of first order logic with very small number of quantifier alternations has been done in a number of papers. I will not go into details here, but just look at one specific case. When we look at automatic structures that admit functions, but we look at quantifier-free formula that may make use of such functions. Then the structure complexity, that is the complexity when we fix the formulae but measures the complexity in terms of the size of the automatic presentation of the structure, has a relatively low complexity, is non-deterministic logarithmic space. When we look at the expression complexity, that is when we look at a fixed automatic structure and measure complexity in terms of the length of this quantifier-free formula, then we can evaluate it in p time, in fact, in quadratic time, and for certain formula, it will be p time complete. And this is important because it generalizes the result mentioned above on automatic groups. Now, the word problem of any automatic group can be solved in quadratic time, and this can be seen as a specific instance of that result, because when we consider an automatic group generated by S1 to Sm, then the Cayley graph is an automatic structure, but the Cayley graph can be seen as a functional structure with the functions mapping a group element to the product with one of the semigroup generation. Now, so by the result above, such a formula can always be a quantifier-free formula on the structure can always be evaluated in quadratic time. And the word problem is, of course, just described by a term equation that is a quantifier-free formula over this Cayley graph. An undecidable problem on automatic structure is the isomorphism problem. Now, since the configuration graph of Turing machines are automatic, it is not a surprise. It's not difficult to come up with specific isomorphism problems in this context that are undecidable. But of course, it is undecidable in a rather strong sense. And this has been proved by Sasha Rubin quite a long time ago, that the isomorphism problem for automatic structure is sigma 1 complete. So it's on the first level of the analytic hierarchy. And interestingly, this is also the case for the much wider class of recursive structures, that is, structures not presented by automata, but structures presented by Turing machine. And in that context, isomorphism is also sigma 1 complete for most of the interesting subclasses of recursive structures, such as recursive linear orders, recursive trees, recursive graphs, recursive Boolean algebras. And it has always been said that if we prove such a sigma 1 completeness result, that this tells us that we have no good characterization of these classes of recursive structures in a sense, in a computational sense. Now, for this reason, quite a lot of research has been done into classifying the complexity of the isomorphism problem for specific classes of automatic structures. So researchers like Kusainov, Kuskeliu, Lorai, Nies, Rubin, Stefan in various combinations have studied the isomorphism problem for specific classes of automatic structures and proved that in some cases these are even decidable, for instance, for automatic ordinals or automatic Boolean algebras. They have the full sigma 1 completeness for linear orders, graphs, and monoids, and in some cases, such as automatic equivalence relations, trees of a fixed height, there is an intermediate complexity in certain levels of the arithmetic hierarchy. So this has been quite an active topic of research inside the field of automatic structures. Now, let me come to the model-theoretic characterization of automatic structures that I mentioned before. So these are really results characterizing automatic structures in terms of first-order interpretation. So a structure is automatic if and only if it is interpretable in one of these universal automatic structures that I mentioned before. So either the expansion of the additive theory of the natural number by a restricted divisibility relation, or into one of these three structures. And we have similar results for the omega automatic structure. So a structure is omega automatic if and only if it is first order interpretable in this specific automatic structure over the real with addition, order, and a restricted divisibility, or in one of these expanded tree structures that may also contain infinite words. So since this is a tutorial, I should perhaps explain a bit closer what I mean by these interpretability results. So an interpretation in some logic from a source signature sigma to a target signature tau is given by a sequence of formula in the target in the source vocabulary that define a universe. So the delta formula would define a universe, the epsilon formula would define an equality relation, and the other formula would define specific relations of a sigma structure. So inside a tau structure B, such an interpretation defines a copy of a sigma structure defined the following way. Take the set of tuples satisfying the delta formula, take the set of relations defined by the formula for the relation, and factor out the equality relation defined by the epsilon formula. Of course, to be well defined, this requires that the epsilon formula defines a congruence relation on the structure with universe delta and the relations divided by phi. But if it does, this is well defined, we take the quotient structure, and this is a structure that the interpretation defines. So in one direction, the interpretation defines a sigma structure inside a tau structure. In turn, the interpretation maps formula of the sigma vocabulary into formula of the tau vocabulary. In the obvious way, just replace single variables by the k tuples of variables that are used in the formula here. Relativize all quantifiers to the domain formula delta x. Replace all equalities by the equality formula, and replace all atomic formulae r or equal to xr by the formulae phi r defining these relations. And the interpretation lemma tells us that this is well defined in the sense that the original formula holds in the interpreted structure if and only if the interpreted formula holds in the original structure. So why is this interesting? So we say that we understand these interpretations as reduction. So L is reducible via L interpretations to B if there is an L interpretation such that as a defining inside B an isomorphic copy of A. And this can be seen as a general and powerful way to define classes of finitely presentable structure with an effective semantics. Just take an arbitrary structure with nice properties, so decidability properties, for instance, and study the closure under L interpretation for some suitable L. Most of the time, one will just use first order logic, but of course, there are contexts where other logics are appropriate. So this closure is a class of structures that admits finite presentations, because interpretations are finite objects and interpretations provide presentations of such structures A. And we also have effective semantics, because if L is closed under interpretations and the logic L is effective on B, then it is effective on any structure that is interpretable in B by the interpretation lemma. So in particular, in the context of automatic structure, we will use first order interpretations. So A is first order interpretable in B, denoted in that way. And by the closure properties of automata, automatic structures and also omega automatic structures are closed under first order interpretations. So if we have a structure that is automatic or omega automatic, and we interpret A inside that structure B by a first order interpretation, then also A is omega automatic or automatic. So in particular, the automatic and omega automatic structures are closed under expansions by definable relations, factorizations by definable congruences, substructures with definable universes, and finite powers. Note that they are, of course, not closed under taking arbitrary substructures, because we may take a substructure with a very complicated, non-definable universe, so this would not preserve automaticity. Now here we get back to the theorem that I mentioned. Such was the case of word automatic structures, and it's now not very difficult to see that this indeed holds. In fact, this follows in a not too difficult way from known results on automata theory. First of all, it is not difficult to see that these various universal automatic structures are mutually interpretable into each other. And so by the closure of automatic structure on the first order interpretation, any structure that is interpretable into one of these universal structures must also be automatic. On the other side, the behavior of finite automata is definable in this universal automatic structure. And for this, we can use a classical theorem from automata theory and logic, usually referred to as a Büchi-Bruyère theorem, that a relation over the natural numbers is regular if and only if it is first order definable in the expansion of Pressburg arithmetic by the function mapping every natural number x to the maximal power of p that divides it. Well, this has been proved a long time ago by Büchi and Bruyère, and it is not difficult to see that also this universal automatic structure and the structure using this function Vp, they are of course very close, and are mutually interpretable into each other. So this provides a purely model-theoretic view of automatic structures, so one could work with automatic structures without ever seeing automata. But of course, it's not desirable to do so, because most of the methods that we have to analyze automatic structures are really based on automata. So let me, for instance, address the questions how to prove that the structure is not word automatic. Now, of course, it is easy if the structure is uncountable and if the theory is undecidable, but what can we do if the structure happens to be countable and happens to have a decidable theory? And one of the methods is based on growth rate. So take an automatic presentation of that structure with bijective function from the regular language into the universe of the structure. Now, fix any set of definable elements ordered by the length of the words that represent them, and take any finite set of definable functions, for instance, the atomic functions on the structure. And then we can define a notion of generations. So the first generation would just consist of the first element A1, and generation n+1 is obtained from generation n by adding on one side the element an+1 and adding all elements that we can produce by applying one of the functions f to elements in the generation n. Now it can be shown by simple automata theoretic results that all elements of the nth generation are represented by words that are linear in n. So the size of the nth generation is 2 to a linear function in n. And it is immediate consequence that, for instance, the multiplicative theory of the natural number is not word automatic, because when we take an enumeration of primes and we take just multiplication as a basic function, then these generations grow too fast. On the other side, it is not too difficult to see that the multiplicative theory of the natural number is tree-automatic. So this result also shows that the notion of tree-automaticity is more powerful than word automaticity. Now, a more sophisticated method to show that the structure is not word automatic is based on well, model-theoretic analysis. And so take an automatic presentation, again, with a bijective way of naming elements by words. And let Cn denote the set of those elements that are named by words of length at most n. Then the result says that this set Cn can only be linearly shattered by first order formula with two free variables. Now, what does this mean? In fact, a result proved by Delorme, again a long time ago, that fix any such automatic structure and fix any formula phi with two free variables, then the number of different subsets of Cn defined by letting the parameter b range over arbitrary elements of the structure and considering the set of A such that phi of AB is true. So the number of different such sets is linearly bounded in the size of Cn. Now, this result, for instance, implies the interesting fact that the random graph is not word automatic. Now, it is known that the random graph is characterized, also called the Rado graph, is characterized by the so-called extension axioms. This means that for every finite set X of vertices and any subset U of X, there exists some node B in the graph that has edges to all nodes in U and to none in the complement of U in X. So this means that this set X is not linearly shattered, but is fully shattered by the edge relation. So the random graph cannot be automatic, because if it were automatic, we could only linearly shatter this set. So there are first structures that are not word automatic, that for which this can be established by similar techniques. So that's a random partial orders, a random Kn-free graph, so it contains no clique of size n. The ordinal omega to omega and all larger ones. And so this, since it is rather easy to come up with an automatic presentation of the smaller ordinals, this also characterizes the word automatic ordinals. These are precisely those below omega to the omega. As a remark, for the three automatic ordinals, the corresponding bound is 1 exponential higher. Now, there is an even more sophisticated result based on the study of arithmetic processions that solved a long-standing open problem proved by Zanko that an additive theory of the rational number is not word automatic. The proof is much more difficult. It's based on a Freiwald theorem of arithmetic progressions, and I will not explain this here. Now, let's now look at the more difficult to analyze class of omega automatic structures. Now, one important difference between word automatic structures and omega automatic structures is that in word automatic structure, we can always assume that we have injective automatic presentation. But this is not so for omega automatic structures. And this is related to an important equivalence relation, the so-called end equivalence of infinite words. We say that two words, X and Y, are end equivalent if they are equal from some position onwards. Now, obviously, this is an omega regular equivalence relation. However, one can show that it does not permit an omega regular set of unique representative. So we cannot achieve injectivity by selecting a regular set of representatives from a given presentation. And in fact, in a LICS paper 2008, Jord, Kusainov, Montalban, and Nice proved that there exist omega automatic structures that do not even permit injective Borel presentations. And Borel presentation is a much more general notion than automatic presentations. So even if we permit much more power in the way how to present such a structure, you cannot present it in an injective way. Now, Fortunately, in the case of countable structure, this difference does not appear. Now, when you have an omega regular equivalence relation that has only countably many classes, then this does permit an omega regular set of unique representative, and an injective omega automatic presentation on a countable structure can in fact be packed into one even over finite words. So this just tells us on uncountable structures there is no difference between word automatic presentations, omega automatic presentations, and injective omega automatic presentation. And this is a quite important result in the study of omega automatic structures due to Kaiser, Rubin, and Barani. And for instance, this tells us that the multiplicative theory of the natural numbers, the additive theory of the rational number, and the random graph, which are all known not to be word automatic, cannot be omega automatic either. Now, moving to uncountable omega automatic structure, the techniques needed to analyze these, in particular analyze the model-theoretic properties and the limitations of definability, are much more sophisticated. So we read results on omega semigroup and Wilke algebras and also some Ramsey theory, which I will of course not explain in this remaining 10 minutes that I have, but I tell you a bit what one can do with such techniques. For instance, we can prove on the minimal image size of definable functions. So in the cases, for instance, when we have a presentation where there is an infinite set of elements represented by words in the same equal end class, then one can show that every first order definable functions, even with counting quantifiers, satisfies the property that the minimal image size of sets of n elements in the structure under such a definable function can only be linear. And this seems like a technical result, but it has a number of consequences for non-automaticity results. For instance, no automatic structure with a definable linear order or an injective presentation can admit a first order definable pairing function. So whenever you have a definable pairing function, you cannot present it in an omega automatic way in this sense. And another result that's been shown by Dietrich Kuske in this context is that the omega automatic ordinals coincide with the omega, with the word automatic ones. So we have not more omega automatic ordinals than we have word automatic ones, and recall that these are below omega to the omega. Now, a fundamental open problem in this field is the question whether the field of reals is automatic in some sense. Well, not in this explicit form, but in some sense, this has already been asked by Rabin. It is, of course, known that the field of reals has a decidable theory shown by Tarski based on quantifier elimination. But contrary to other such structures, such as Pressburg arithmetics, where we have automata-based decision procedures, we do not know such a procedure in the case of the field of reals. Now, clearly, since this is an uncountable structure, it cannot be presentable by automata or finite words or finite trees, but it could a priori be omega automatic or omega 3 automatic. And in fact, it is not difficult to see that both the additive and the multiplicative reduct do admit automatic presentations even over infinite words. So one might hope that we could combine these to a presentation of the entire field. And for the case of automata over infinite trees, or a more general object, this is still open. We do not know whether it is the case, but we can show that the field of reals is not omega automatic. And to prove this, we seek a classification of all omega automatic fields. So in fact, a bit more generally, we consider not fields, but integral domains, that is commutative rings without divisors of 0, and we classify the omega automatic integral domains. So first of all, the word automatic ones had already been classified in a LICS paper by Kusainov, Nies, Rubin, and Stefan back in 2007. And in some sense, this is disappointing. See, word automatic integral domains are precisely the finite ones. Now, finite structures are always word automatic, so that tells us there are no interesting word automatic integral domains. So this, of course, also implies that there are no countably infinite omega automatic integral domains, because by the result, by Barani, Kaiser, and Rubin, these would have to be word automatic as well. And we know that there are no infinite word automatic integral domains. So the question is, are there uncountable ones? And for this, again, we use a model-theoretic property that itself is not easy to prove, but very useful. And it says that for every uncountable omega automatic structure, there is some natural number k, such that every first-order definable function with k plus 1 argument is constant on some set m times n, where m and n are uncountable sets. Now, assume that we would have an uncountable omega automatic integral domain. Then for every k, the polynomial with coefficients a and indeterminate x is definable. So hence, there exist two different polynomials, that is, two different strings of coefficients, such that f of ax equals f of bx, even for uncountably many x's. But this cannot be the case, because two different polynomials of degree k minus 1 can agree on at most k minus 1 inputs. So we have a contradiction. So there do not exist any uncountable omega automatic integral domains. So we have that an integral domain is omega automatic if and only if it is infinite. So in particular, the field of reals is also not omega automatic. Finally, let us look at one further class of automatic structures. These are automatic structures with advice. So we look at automata that do not just have their usual inputs, but they have an additional advice input that they can access. So the advice can just be assumed to be a fixed infinite word. And although it is known that the additive structure of the rational number is not automatic, it has been shown that it is automatic with advice. And in fact, the notion of automaticity with advice is still a useful class of automatic structure, because if we impose the additional condition that the advice string is not arbitrary, but it is an advice string that itself has a decidable monadic second-order theory, then one can show that the first-order theory of the structure that is presented this way is still decidable. And with this advice, there comes a further interesting twist. We can now lift the notion of an automatic presentation to classes of structures. So we take a fixed collection of automata, but we vary the advice. So then we present for each advice a separate structure, so we can have an automatic presentation of an entire class of structure. And we call a class of structures strongly omega automatic if it is presentable by automata over infinite words with an advice set that has a decidable monadic second order theory, and we even call it regularly omega automatic if the advice set is an omega regular set. So these would still be classes of structures that have decidable first order theories. And there are interesting examples, for instance, the torsion-free abelian groups of rank 1, which up to isomorphisms are the subgroups of the additive group of rationals, form such a regularly automatic class. So this is a possibility to extend the notion of omega automatic structures in some way, but it does not solve all problems. For instance, the field of reals, this will not help for the field of reals. It is also not omega automatic with advice. So the problem whether there is some kind of automatic presentation of the field of reals is still an open problem. So let me end here and just display a list of thanks to many people. Thank you very much.
Thank you very much, Erich. So I think, I don't know what we're doing for virtual clapping, but let me at least clap that. That was very, very informative. So can I ask, so those of people on Zoom, we're going to take some questions now and then proceed to a break, but can those people on Zoom can, I guess, type their questions into the chat, and I guess other people can type them through Slack and Joel will forward them. So
there are no questions on Slack at the moment, but perhaps Erich, first, thanks for a very informative tutorial. I think I found myself wishing that sometimes I could just pause and just stare at the slides for a little bit. It was coming a little bit at speed for me, but fascinating tutorial. Just a question. So the additive group structure of the rationals is not omega automatic, but the additive reals is. And somehow I find this counterintuitive. Can you comment on this?
Mm. Well, I mean, this is, it's just that for countable structures, omega doesn't really help anything. I mean, I do not remember precisely how the. So it is. I mean, it is not difficult to come up with an automatic presentation of the additive group of reals by taking an infinite presentation of the real by an infinite string of zeros and ones, right? But it's very hard to put this down to the rationals.
So because I mean, I have the intuition that if you're, let's say, adding two rationals that are periodic, then the sum is going to be again periodic. And so whatever worked for the reals should still work here. But is it some condition that one needs to a priori impose periodicity? Or I guess I just don't have a good sense of how these things work, but it just seems very counterintuitive to me. You'd think whatever works for the real.
Well, you said that arbitrary substructures are not, I mean, automaticity is not inherited by substructures.
No, that's true, and that obviously would have to be the case, but it's still counterintuitive somehow.
Yeah.
Okay, I mean, so to prove that it is not automatic is quite hard to prove, right? So it's not something that you do.
I see.
But I did think about why the obvious approach would fail.
Well, I mean, but how do you even know that a name is a rational number? How do you know that a string is named?
No, you don't. But you just have the automaton just doing the.
Yeah.
Okay. I guess I chose.
So are there any questions?
There are no questions on Slack, and there are no questions in the chat. So perhaps people can try raising their hands. And there are no hands raised.
I have a question. I was first of all, you mentioned that the first order theory of the structure with n plus and this divisibility by powers of p.
Yes.
You mentioned it was non-elementary, the decision problem, but you didn't give a reference. I'm just wondering where that is proved.
Well, I mean, there's a paper that I wrote a long time ago on simple interpretation of complicated theories where this is proved, but I don't think I'm not sure it was really the first time that it was proved. I mean, it's these structures are just powerful enough to probably it would also follow from all results by Meyer and Stockmeyer on
okay.
On structures that are closely related to automata, but it's certainly explicit in that old paper of mine on simplification of complicated theories.
And just, well, are there any questions, Joel? Otherwise, I indulge myself in it. You're muted.
I mean,
no questions. No questions and no hands raised, but
okay. So let me just indulge with another question. You said that if you're interpretable in n plus and with this p divisibility for one p, then you are for all p. But I don't see why this is. I mean,
I mean,
is it trivial? Or?
To do it, I mean, I'm sure you can do it directly, but you can, of course, go through the automaticity result. So you would have to switch between two different presentations, right? So one is obviously automatic when you take P array representation, and one is when you take a Q array representation, right?
Yeah,
and you have to be able to switch between these two presentations.
Okay.
Which in, let's say, this does not work in all generality, but for this.
Yeah. Yeah. No, you're right. Sorry, you're right. If you're P, sorry, if you're P regular, yeah. Okay. Yeah. Okay.
There is a question from Clemens Kupka. Perhaps I can just read it because I didn't have time to copy it. He's asking, is there any connection to automata learning? Can one learn the representation of an automatic structure?
I don't know. So I haven't studied it, but I think one should be able to do something here, because I mean, this is so closely related to structures like Pressburger arithmetic that I'm not sure that you can do it for all automatic structures, but certainly you can do it for interesting ones. And this certainly is something that one should look into. But to be honest, I haven't studied it.
Okay, so maybe one more question if there's time.
There are none forthcoming that I can see, but
okay.
Yeah.
Well,
another one, Joel?
No, sorry. There are no questions I can. Sorry, I'm monitoring the various sources where questions can come, and I don't see any. I hope I'm not messing up. I don't see any.
Okay, so if there are no more,
sorry, there is a question. There is a question. Do you want to read it, Ben?
Yeah. So the question is, what is the meaning of the term interpretability of automaticity with advice? So, well, I get, yeah. So I hope I'm parsing that correctly. So, what is the meaning of the terms interpretability of automaticity with advice? I'm not sure whether there are two questions there or.
No, and one has this. We would have to think about it. So we didn't come up with a precise definition here. I mean, I'm sure one can come up with a notion of interpretability, and we would need that to put into the notion of interpretation. You would have to put that notion of advice into it, for instance, by additional components. But
oh, I see. So the question is this notion of automaticity with advice? Can you understand it in terms of FO interpretability?
Yes.
Yeah.
And
okay.
I'm not sure this has been done explicitly. I don't think it has, but well, I cannot think of any immediate obstacle to that. One has to, of course, tune the definitions, but yes, I mean, it's a good question, right? One should make this explicit. So, I mean, it's a question whether one can still find interesting complete structures in that sense.
So in the sense that n plus and divide by p is complete for automaticity, word automaticity.
Well, either we have to change the notion of the interpretation, but we stick to first order interpretation and generalize the structure. So again, the honest answer is I don't know.
Okay, but that sounds like a very interesting question. So I think we should wrap up now. So I think Holger is going to tell us what's going to happen now? Or...
I would like to thank our invited tutorialist for this great talk. I cannot tell you a lot. The session, let's say the invited tutorial now ends, but we have decided to leave the Zoom link open for people that want to just chat. So because yesterday in the social meeting, there was some intention to have a bit more options for interaction. So the channel will stay open, so to speak, until the next Q&A starts, which is in like 22 minutes. So if people want to chat, they can just do this. But I guess now that the discussion has ceased, we close the tutorial. And I guess on behalf of everyone, let me thank the invited tutorialist, Erich. Thank you.
Thanks to all of you.
Okay, so I guess people can unmute themselves if they want.
Yeah, they can absolutely unmute.
Chit chat.
If they want. They're not forced, but they can.
Should I leave the screen out? The shared screen out?
No, I guess we can stop the screen share. Then people see a bit more of the
Okay.
other.